Introduction. Hello students.
Good morning, sir.
Very good morning. Today we will perform an experiment to identify the acidic, basic or neutral solution.
Fine, sir.
First, put a drop of solution 1 on the blue litmus paper. It turns into red. It shows acidic behavior. Next, put a drop of solution 2 on the red litmus paper. It turns into blue. It shows basic behavior. Finally, we test for solution 3. The color is not changing. It shows that this solution is neutral, and we can say that solution is at equilibrium.
Sir, what is equilibrium?
Equilibrium is a condition when the number of moles of base becomes equal to number of moles of acid. Let's learn more about it. In this lesson, you will study the physical and chemical equilibrium. Objectives. At the end of this lesson, you will be able to explain ionic equilibrium in solution, discuss the concept of acid, bases and salts, explain pH scale, discuss factors affecting acid strength, discuss hydrolysis of salts and pH of their solution, define buffer solution, define solubility product constant. Ionic equilibrium in solution. The aqueous solution of substance such as sodium chloride, sulfuric acid, etc. conduct electricity, whereas aqueous solution of sugar, urea, etc. does not conduct electricity. The substances which conduct electricity in their aqueous solution are called electrolytes. On the other hand, those which do not conduct electricity in their aqueous solution are called non-electrolytes. The electrolytes which almost completely ionized in their solution are called strong electrolytes. On the other hand, the electrolytes weakly ionized in their solutions are called weak electrolytes. The equilibrium which involved ions in aqueous solution is called ionic equilibrium. Acids, bases and salts. Electrolytes may be acids, bases or salts. Acids are sour in taste. Vinegar contains acetic acid. Tamarind contains tartaric acid. Acids turn blue litmus paper into red. Bases are bitter in taste. They turn red litmus paper into blue. Caustic soda, washing soda are commonly used bases. Arrhenius concept of acids and bases. An acid is a substance that when added to water increases the concentration of H+ ions, whereas base is a substance that when added to water increases the concentration of OH- ions. Acids such as HCl and HNO3, which are most completely ionized in aqueous solutions, are termed as strong acids, whereas acids such as CH3COOH, which are weakly ionized, are called weak acids. Similarly, bases which are almost completely ionized in aqueous solution are called strong bases. For example, NaOH and KOH. The bases such as NH4OH are only slightly ionized and are called weak bases. H+ ion is formed by the loss of electron, therefore it is simply a proton and cannot exist independently. So it is considered to be present in hydrated form in combination with water molecule as H3O+. H3O+ ion is called hydronium ion. Similarly, hydroxyl ion is hydrated to give species such as H3O2- ions. The Bronsted-Lowry acids and bases. According to them, An acid is a substance that can donate a proton. A base is a substance that can accept a proton. Conjugate acid-base pairs. In the forward reaction, water donates a proton to ammonia, base, and acts as acid. In the reverse reaction, NH4 plus ions donate a proton to the OH minus ions, base, and act as acid. A base formed by the loss of proton by an acid is called conjugate base of the acid, whereas an acid formed by gain of a proton by the base is called conjugate acid of the base. In this example, OH minus is the conjugate base of H2O and NH4 plus is conjugate acid of NH3. Acid-base pairs such as H2O, OH minus and NH4 plus by NH3, which are formed by loss or gain of a proton, are called conjugate acid-base pairs. Example: write the conjugate acids for the following Bronsted bases: H2O, NH3 and C2H5OH. Solution: the conjugate acid is formed by gain of a proton by the base. Thus, the conjugate acids of the given bases are: for H2O, conjugate acid is H3O+. For NH3, conjugate acid is NH4+. For C2H5OH, conjugate acid is C2H5OH2+. Lewis acids and bases. According to Lewis concept, an acid is a substance which can accept a pair of electrons. A base is a substance which can donate a pair of electrons. For example, in the reaction, BF3 acts as acid. Ionization of acids and bases. The ionization constant of water and its ionic product. Pure water itself is very weak electrolyte and ionizes according to the equation, or simply written as, for which the ionization constant is given by Ki is equal to concentration of H plus into concentration of OH minus by concentration of H2O. As water is poorly ionized, its concentration is found to be poorly ionized. Its concentration can be combined with the ionization constant, Ki, to give a new constant, known as ionic product of water, Kw. Name it as equation 1. The concentration of OH minus in pure water is same as that of H plus. Therefore, Kw is equal to H plus square. The value of H plus in water at 25 degrees Celsius is found to be 1.0 into 10 raised to the power minus 7 m. The value of ionic product at 25 degrees Celsius is thus equal to 10 raised to the power minus 14 m square. From equation 1, for neutral solution, concentration of H plus is equal to concentration of OH minus is equal to square root of Kw. For acidic solution, concentration of H plus is greater than concentration of OH minus. For basic solution, concentration of H plus is less than concentration of OH minus. The pH scale. pH of a solution can be defined as negative logarithm of hydrogen ion concentration. For neutral water at 25 degrees Celsius is given by pH is equal to minus log of 1.0 into 10 raised to the power minus 7, which is equal to 7. The pH corresponding to the acidic and basic solution at 25 degrees Celsius will be less than and greater than 7 respectively. We can define pOH scale as the negative logarithm of hydroxyl ion concentration. Both pH and pOH are related to each other through the expression pH plus pOH is equal to pKw. The value of pKw is 14 at 25 degrees Celsius. pKw controls the relative concentrations of hydrogen and hydroxyl ions as their product is a constant. Ionization constants of weak acids. Consider a weak acid HX that is partially ionized in the aqueous solution, and it can be represented as: let initial concentration of HX be C. Let alpha be the extent of ionization change, so equilibrium concentration of HX is C minus C alpha. H3O plus equilibrium concentration is plus C alpha, and X minus equilibrium concentration is plus C alpha. The equilibrium constant for the reaction is Ka is equal to C square alpha square by C into 1 minus alpha. Ka is equal to C alpha square by 1 minus alpha. Ka is called the dissociation or ionization constant of acid HX. It can be represented in terms of molar concentration. The pH scale for the hydrogen ion concentration has been extended to get ionization constant of weak bases. The ionization of weak base XOH can be represented as: the equilibrium constant for base ionization is represented by Kb and is called as base ionization constant. It is given as: if C be the initial concentration and alpha be the degree of the ionization of base, so the equilibrium constant can be written as Kb is equal to C alpha square by 1 minus alpha. The pH scale for the hydrogen ion concentration has been extended to get relation between Ka and Kb. The equilibrium constant for a net reaction is the product of equilibrium constant for individual reactions. It can be represented as K net is equal to K1, K2, K3, so on. For conjugate acid-base pair, Ka, Kb is equal to Kw. Di- and polybasic acids and di- and polyacidic bases. The acids which contain more than one ionizable hydrogen atom in a molecule are known as polybasic acids. For a dibasic acid, H2M, name it as reaction 1. Name it as reaction 2. The equilibrium constant for the reaction 1, Ka1 is equal to H plus into Hm minus by H2M. Ka1 is called the first ionization constant. The equilibrium constant for the reaction 2, Ka2 is equal to H plus into M square minus by Hm minus. Ka2 is called the second ionization constant. Ka1 is greater than Ka2 because of more electrostatic force. Factors affecting acid strength. Bond strength. The strength of the bond between the acidic proton and the rest of the molecule will have an effect on acidity. The weaker the bond, the more acidic the acid will be generally. Bond polarity. A highly polar bond between acidic hydrogen and another atom tends to make it easier for the proton to leave the molecule and makes it more acidic than would happen for a non-polar bond. For acids of elements in the same row, the bond strength tend to be more similar to each other, and so the polarity of the bond plays a greater role in determining acid strength. Since polarity depends on the electronegativity of the atoms involved, acid strength tends to increase with electronegativity because the bond tends to be more polar. Common ion effect in the ionization of acids and bases. The common ion effect is the shift in an ionic equilibrium caused by the addition of a solute that provides an ion that takes part in equilibrium. Consider the solution of acetic acid, HC2H3O2. If we add HCl aqueous to this solution, HCl aqueous is a strong acid. It provides H3O plus ion, which is present on the right side of the equation for acetic acid ionization, according to the Le-Chatelier's principle.
The equilibrium composition should shift to the left.
The degree of ionization of acetic acid is decreased by the addition of a strong acid. This depression of the ionization of acetic acid by HCl is an example of the common ion effect. Hydrolysis of salts and pH of their solutions. Hydrolysis is a process in which water reacts with salt to form an acid and a base. Salt of weak acid and a strong base. The hydrolysis of a salt MX of this type. In solution MX, the strong base MOH undergo complete dissociation, whereas acid HX, being weak acid, remains almost undissociated. The pH of the solution of this type is more than 7. Salt of strong acid and weak base. The hydrolysis of a salt MX of this type. In solution MX, the strong acid HX undergo complete dissociation, whereas weak base MOH remains almost undissociated. The pH of the solution of this type is less than 7. Salt of weak acid and weak base. The hydrolysis of a salt MX of this type. In solution MX, the weak acid HX and weak base MOH both remain in partially dissociated form. The pH of the solution of this type is pH is equal to 7 plus 1 by 2 into pKa minus pKb. If the value of pKa minus pKb is positive, then the pH is more than 7, and if the value of pKa minus pKb is negative, then the pH is less than 7. Buffer solutions. A buffer solution is defined as a solution which resists a change in pH on addition of small amount of acid or base. Buffer action. The ability of buffer solution to resist change in pH on addition of acid or base is called buffer action. A strong acid such as nitric acid or hydrochloric acid can act as a buffer with a low pH. Solubility equilibria of sparingly soluble salts. The solubility depends on the lattice enthalpy of the salt and the solvation enthalpy of the ions in a solution. Solubility product constant. For any sparingly soluble salt which dissociates to set up the equilibrium, the solubility product constant may be defined as concentration of AY plus raised to the power x into concentration of Bx minus raised to the power y, whereas Ay plus and Bx minus denote the positive and negative ions respectively, and X and Y represent the number of these ions in the formula of the electrolyte. Thus, the solubility product of a sparingly soluble salt at a given temperature may be defined as the product of the concentrations of its ions in the saturated solution, with each concentration term raised to the power equal to the number of times the ion occurs in the equation representing the dissociation of the electrolyte. Knowing the solubility of the salt, its solubility product can be calculated. For example, consider the salt AB. Suppose at a particular temperature, its solubility is S mole L-1. S moles of salts on ionization will give S moles of A plus and S moles of B minus. KSP is equal to concentration of A plus into concentration of B minus is equal to S into S is equal to S square. Common ion effect on solubility of ionic salts. If NaCl solution is added to AgCl solution having Cl minus as common ion, solubility of AgCl will decrease because Cl minus from NaCl will combine with Ag plus to form AgCl. Similarly, if concentration of one of its ion is decreased, more salt will dissolve to increase the concentration of both the ions till once again KSP is equal to QSP. It is applicable even to NaCl, which is completely precipitated by increasing Cl minus using HCl gas through NaCl solution. The common ion effect is also used for almost complete precipitation of a particular ion as its sparingly soluble salt with very low value of KSP for
gravimetric estimation by mass determination.
Did you know? Strong acids are highly corrosive, such as sulfuric acid. They can dissolve metals. A base that dissolves in water is called an alkali. When you add an acid to an alkali, both are neutralized. The acid and alkali react together, forming water and a salt. Summary. Let us summarize what we have learned. The equilibrium which involved ions in aqueous solution is called ionic equilibrium. According to Arrhenius, an acid is a substance that when added to water increases the concentration of H plus ions, whereas base is a substance that when added to water increases the concentration of OH minus ions. According to Bronsted and Lowry, an acid is a substance that can donate a proton. A base is a substance that can accept a proton. A base formed by the loss of proton by an acid is called conjugate base of the acid, whereas an acid formed by gain of a proton by the base is called conjugate acid of the base. According to Lewis, an acid is a substance which can accept a pair of electrons. A base is a substance which can donate a pair of electrons. pH of a solution can be defined as negative logarithm of hydrogen ion concentration. Hydrolysis is a process in which water reacts with salt to form an acid and a base. A buffer solution is defined as a solution which resists a change in pH on addition of small amount of acid or base. The solubility product of a sparingly soluble salt at a given temperature may be defined as the product of the concentrations of its ions in the saturated solution, with each concentration term raised to the power equal to the number of times the ion occurs in the equation representing the dissociation of the electrolyte.